Morning, guys. Today we're going to be looking at section 13.3 from our textbook, which continues our journey into trigonometry and talks more about those angles in the coordinate plane, those kind of circular angles that we looked at in the last lesson, both in degrees and radians. And finally, we get to start seeing how will we know what some trig functions are just based on what we see in those angles. So I'm going to grab my pen. Screen is shared, and let's start talking. So first note, and this is a note that we're going to talk about briefly right now, do a little bit of practice with, and then come back to later on in the lesson. It has to do with reference angles. And if you look at this little symbol up here, this is right here pronounced theta. That's that Greek symbol again, theta prime. And when you see that little apostrophe up there, that's what that signifies. Theta prime is what we usually use for a reference angle. So what is a reference angle? Well, it's going to be used for reference. You might have figured that out, but it represents the shortest distance of our terminal side back to the x-axis or forward to the x-axis potentially. And so when you're thinking reference angles, when you're thinking theta prime, the biggest thing you want to think about is, well, how far from the x-axis am I? Let's look at some examples. So right here, we have an angle in quadrant 1, and theta is 50 degrees, and we're asked for theta prime. So there are two ways we could get to the x-axis. We could go kind of back this way, or swing all the way around to the left. Now, our first question is, which one of those is the shorter distance? Well, just the eye test, knowing we're in quadrant 1, going back to the x-axis is going to be the shorter distance, right? And so the question is, how far do we have to travel? Well, we went up 50 degrees to form this angle. That means that to get back, we should just travel backwards 50 degrees. Theta prime in this problem is 50 degrees. And as it turns out, for any angle, I shouldn't say any angle, for any angle between 0 and 360 degrees within the first quadrant, theta prime is just going to be our theta. We're just going to retrace our steps to get back to the x-axis. But what about this second example on the screen right now? We're in quadrant 2 right now, and we're told right now that theta equals 7 pi over 9. So theta equals 7 pi over 9. If you remember those radians, 0 and 2 pi is a full circle, and so pi is over here. So in radians, the problem was given to us in radians. What is our reference angle? Well, again, think about the two ways we could get back to the x-axis. Instead of going the long way like we did on that previous problem, we probably want to go forward in this case. And that's the shortest distance to get to the x-axis. So we find our shortest distance. We say, okay, so 7 pi over 9 is where we are. I'm going to write that over here kind of by my terminal side. How far do we have to go to get to the x-axis? Well, that question could be rephrased as, how far do we have to go to get to pi? Because remember, pi is sitting right here on the x-axis. So how far do we have to go from 7 pi over 9 to get to pi? So I like to think of it and say, okay, 7 pi over 9, and I'm trying to get to 9 pi over 9. And you might have seen what I did just there. I'm trying to get to pi. That's 9 pi over 9 is just pi. But I wrote it with a common denominator because now I say 7 pi over 9 plus what equals 9 pi over 9. And I can see a little more easily 2 pi over 9. If I travel 2 pi over 9 radians, I will get to 9 pi over 9, that's pi, that's my x-axis. So you're going to be seeing questions that ask you about reference angles in degrees and in radians, and we have to be familiar with each. In this problem, we just said, how can we get to the x-axis? How can we get to pi? We need another 2 pi over 9. I would like you to pause your video, think about what we've said already and just jot down answers. Try to do these next two problems for quadrant 3, quadrant 4. When you're done, unpause it, and I will kind of talk through and still work these out with you. So go ahead, pause, give them a shot, then unpause. And by now you have done just that. You have paused it, given it a shot, and here we go together. 210 degrees. We know that this was 0, 90, 180, and down, straight down is 270, so we're not there yet. So 210 falls in quadrant 3. So to get to the x-axis, shortest distance, should I go this way or that way? To the right, to the left, shortest distance, I should definitely go to the left. So I'm currently at 210. I'm trying to get back to 180, my x-axis. So 210, and I need to go to 180. My theta prime is going to be 30 degrees because I'm traveling 30 degrees to get there. Now this might bring up a question. I want to try to address a possible question people might be asking, which is, should it be negative 30 degrees? And the answer is no, because a reference angle represents a distance. And distances, by nature, the way we kind of define them, they're always positive, right? Or zero. If you live 2 miles north of school, you say, I live 2 miles away. If you live 2 miles south of school, you still say, I live 2 miles away. You don't say, I live negative 2 miles away. That doesn't really make sense with our common understanding. So reference angles or distances, they are always positive. And that's why here we need to travel 30 degrees, kind of in the backwards direction, but 30 degrees to get back to the x-axis. And so that is my reference angle. Hopefully on this fourth one, you got a little bit of practice with radians. We're at 14 pi over 9. We could go back, we could go forward. We want to choose the smallest one. So I'm going to go forward. And so I'm going from 14 pi over 9, and I need to get to 2 pi because that was a full circle, right? So getting to 2 pi, that means I'm trying to get to 18 pi over 9, getting a common denominator. And so what would it take to get me from 14 pi over 9 to 18 pi over 9? It would take me 4 pi over 9 radians. So that's what a reference angle is, all right? A reference angle is simply how far do we have to travel in whatever unit we're given the angle to get back or forward to the x-axis. How can we get to 0? How can we get to 360? How can we get to 0? How can we get to 2 pi? Or 180, I realized just now, I skipped 180. 180 is on that left-hand side of the x-axis. So 180 or pi as well. So what I would like you to do is pause. I'm gonna pause and work these out and put the answers on the screen. I'm gonna start by sketching each of these, try to figure out where they are. And so that 275, you might kind of know where it is, but what about that 20 pi over 3? Just like we did last lesson, trace it out. It's going to be more than one revolution. See where it ends up. And as soon as you know where that terminal side ends up, it's just like any other reference angle problem. But pause your video. I'm going to pause my video, work them out, and then I'll have the answers on the screen here in a second. We'll talk them through. Try to get these answers down yourself. All right, so I have my 4 problems worked out on the screen. And in blue was a lot of my work related to the reference angle. I'm trying to tell you how I color coded it a bit. We've got some red and purple on there as well. I will talk through these and hopefully if you weren't getting the same things I was, give you a good idea of how I got them. So the first one, 275 degrees. First thing to do is figure out where on our coordinate plane does that land. Well, I know that every quarter of the circle is 90 degrees. So if you're looking, we got 0, 90, 180, 270 is straight down. So 275 would be just a tiny sliver past that. So 275 is in quadrant 4. And so it's going to be quicker to go forward to 360 than it is back to 180 because we're already in that quadrant 4. And so we can say 275 to get to 360, how far would I need to go? I just did some simple subtraction. 360 minus 275 equals 85 degrees. If I travel forward 85 degrees, I will hit the x-axis that is my reference angle. That's my theta prime. A much more difficult one now was over here to the right, 20 pi over 3. Now, thinking about that very first step, you can see, I mean, the spirals, they look a little trippy right now, but that first step is, where does this land on the coordinate plane? So here's what I did. I said 20 pi over 3. Well, I could break that into 18 pi over 3 plus 2 pi over 3 if I wanted. That's still 20 pi over 3. And why did I do that? Because 18 pi over 3 is just 6 full pies. I was looking for like that closest full pi measure. So 6 full pies told me that's 3 full circles. That's 3 2 pies. So 1 full circle, 2 full circles, 3 full circles. And then in purple, that was my 2 pi over 3. After my 6 full circles, I just need to go 2 pi over 3 more. So that's kind of 2/3 of the way to pi. 2/3 across that top half of the circle. So that lands up where purple shows on the graph, which means I need to go theta prime, go forward towards pi. Well, I did 6 circles and then 2/3 of the way there. So over here on the left, I said I'm at 2 pi over 3 basically. It's a coterminal angle. I'm trying to get to pi. Pi could also be written as 3 pi over 3. So how do I get from 2 pi over 3 to 3 pi over 3, excuse me? I go 1 pi over 3. That'll be my theta prime. That'll carry me all the way to pi from that leftover 2 pi over 3 I had after my 6 circles. The other two, if those two make sense, the top two, the other two should come pretty nicely. 500 degrees, more than a full circle. So I said, well, I could take away a full circle, 360s in red, and then just go 140 degrees. That's not quite all the way to the 180 that I needed. So I went another 40 for my reference angle. And then 3 pi over 4 is 3/4 of the way to pi. Not all the way there, but it's quicker to go forward to pi than back to 0. So how do I get from 3/4 pi to pi? Just go another pi over 4 as my reference angle. I'm going to be referring back to this in a little bit, this idea of reference angles getting to the x-axis. But it's, in addition to just being good for reference angles, it also helps build our understanding and our thought process of where are these angles on the graph? What are coterminal angles? 500 is coterminal with 140. We can just go a full circle and then it's 140. So kind of a valuable exercise to build familiarity with this coordinate plane angle system that we haven't really seen much before. So now we're going into something a tiny bit different. I mean, still trig, absolutely. Still everything still applies, but not reference angles. Now we're going to look at this alternate definition of SOHCAHTOA. And this is the definition we are going to use anytime we're in the coordinate plane. So if you're looking at the screen right now, it says let theta be an angle in standard position, and let P, x comma y, so point P, be a point on the terminal side of theta. And I say note that R stands for the radius and is the hypotenuse of the triangle formed. Well, then the trigonometric functions of this angle may be defined as follows. And right now, you want to pause the video and you want to write these down, what I just boxed in red. Sine of theta is y over r. Cosine theta is x over r. Tan theta is y over x, provided that x doesn't equal 0 because we can't divide by 0. Cosecant we know is just sine flipped, so r over y. Secant is r over x, that's cosine flipped. And then cotangent is x over y, again making sure that none of those denominators are 0. So if you need to pause the video right now, take those down. I'm going to keep talking because I assume you paused them and got them down. Here's what we're going to use with these is if you look at the problem right below, we have a point. P is 4, 2. We went over 4 in the x direction, up 2 in the y direction to form our theta. And so we're asked, what is sine of theta? What is cosine, tangent, cosecant, secant, cotangent of theta if theta goes through that, or if the terminal side goes through that point? Well, here's what we're going to do. On this problem, I know that x equals 4. You want to know how I know that? Because we were told right here in the point that the x coordinate is 4. And I know that y equals 2. I went up 2, and it shows me right in the point here, the y coordinate is 2. So for these definitions, we need 3 things. We need x, we need y, and we need r. So how do I find r? Well, the key is remembering that the x and the y, I mean, those two sides of the triangle intersect at a 90-degree angle, meaning this is a right triangle, meaning I can say that 4 squared plus 2 squared is going to equal r squared. R is the hypotenuse of this triangle. R stands for radius because it's something called the unit circle that you're going to see a lot about here later this lesson. But that's r. So 4 squared plus 2 squared equals r squared. 16 plus 4, so that's 20 equals r squared. So r equals, and I know that 20 can probably be broken down. 4 and 5, 2 and 2. So 2 root 5. Finding that r is going to be the first thing you need to do on these problems, because once you have x, y, and r, it's just plug and play. Sine of theta equals y over r. So y over r is 2 over 2 root 5. And I can simplify that to 1 over 1 root 5, or just root 5. And then I don't want that radical on bottom. We know that. So I'll use the trick we've been seeing a lot of, multiply by root 5 over root 5, and that gives me root 5 over 5. Sine theta on this problem equals root 5 over 5. Now, back in 13.1, I talked a little bit about, okay, I know that cosecant and sine are linked. I know that I can just flip sine, but I'm not gonna flip my final result for sine because then I'd have a radical on bottom. I'm actually gonna look back in the problem and say, you know what? This is the step I probably want to flip, because that gives me root 5 over 1, which is just root 5. And then I don't need to do any extra work getting another radical out of the denominator. So work smarter, not harder, and look for ways to kind of simplify our process. What about cosine? Cosine theta, we know, is x over r. And so x, I have written over here to the side by my star, x was 4 over 2 root 5, was r. So that's 2 over root 5. I'm dividing both top and bottom by 2, multiply by root 5 over root 5. And we get 2 root 5 over 5. Cosine theta, 2 root 5 over 5. Now, cosine and secant are linked. I'm looking. I think I probably want to just flip this guy because then the radical ends up on top. So I'm going to say secant is root 5 over 2. Done and dusted. Last one, tangent. From our definitions up top is y over x. So y over x, and then over there I had written off to the side, y was 2, x was 4. No radicals, that's just 1/2, 1 over 2. And then cotangent, which goes along with tangent, 2 over 1, or just 2. In a second, I'm going to ask you to pause and try one of these yourself. But it comes down to finding r using the Pythagorean theorem. You have the x and y coordinates from your point, use them to find r, Pythagorean theorem. And then just going off the definitions that we have in that red box, list out and simplify all of your trig functions, your trig values, I should say. So there's 2 more things I want to talk about. One of them is, how do we remember which one is which? Why is sine y over r? Why is cosine x over r? So I have a way to remember those 2. I know that they're y over r, x over r. R is on bottom for our two main ones, sine and cosine. But which one's which? Well, in my mind, sine and y rhyme. I mean, they basically do. Sine, y. People tell me all the time they don't, but in my mind, they basically do. They're close enough. Sine is y over r. Cosine is x over r. I know it doesn't rhyme, but that's okay. X can't go with sine because they don't rhyme. Sine is y over r. Cosine is x over r. Tangent is y over x, the sine over the cosine. And then the other three we know are just flipped values. So you'll need to know these kind of off the top of your head. So figure out a way, maybe you remember that sine and y rhyme, so sine is y over r, but figure out a way to memorize these. The other thing I wanted to talk about on this one is, what is theta? How can I find this angle given this information? Well, this goes back to 13.1. And here's what I'm going to say. I'm going to look at my angle up there and say tan theta equals y over x. So tan theta is equal to 2 over 4. And if you remember, how do we undo a tangent? By hitting it with an inverse tan. I'm going to write it down here because I kind of ran out of room up there. I didn't leave myself room. That was poor planning. But inverse tan will get rid of my tan, will leave me with theta equals inverse tan of 2/4. And once we have that, we can just come to our calculator and use that inverse tan functionality, that inverse trig. So my calculator boots up. I say second tan, so inverse tan, 2 divided by 4. And it tells me 26-ish degrees. Rounding to the nearest degree like we usually do, that'll be 27. And before I move on from this problem, I like to look and say, does that look like it could be a 27-degree angle? Yeah, I mean, first quadrant, up from the x-axis a little bit, 27 degrees looks good. So kind of a lot of steps, I know, I realize, but I want you to duplicate those steps right down here with this problem. Notice that your triangle is not really drawn in. I'm going to draw it back to the x-axis for you. There's your triangle. You went 6 in the negative direction. And I know I just got done talking about how distances aren't really negative, but the coordinate is negative. So we probably want to include that -6 down there. Here's a 2. I want you to pause the video, find r, list out your 6 trig functions, try to find theta. I'm going to do the same. We'll compare answers in a sec. All right, so not talking through this one 100% step by step, but when I solved for r using Pythagorean theorem, I got 2√10 simplified. And so you can see those trig ratios over there on the right. Sine is y over r, 2 over 2√10, and then 1 over √10. We know we multiply by √10 over √10, so we get √10 over 10. That was a lot of 10s I just said. And then I filled in cosecant, which is the reciprocal of sine, with √10 over 1 or just √10. Cosine is -6 over 2√10, -3 over √10. And I want you to just notice right here, I'm hoping you're getting to the point where what I'm circling right now, we know we need to multiply by √10 over √10. And so we know that'll give us -3√10 on top over 10 on bottom. Unlike above in purple where I wrote it out multiplying by √10 over √10, if you are starting to see these patterns and it becomes automatic for you, you don't have to write out what you're multiplying by in this specific instance. I know I'm always on you guys about showing your work, showing every step, but this is one of those things where if we do it 5, 10, 100 times this chapter, then it's okay if you've done it the first 50 showing your work. I know that the next 50 you know what you're doing and you can go straight to -3√10 over 10. You can see my other 4 trig values there. Tangent came out nicely with no radicals at all. the funny thing happened when I got to theta. And theta, well, I know that theta is y over r, sorry, tan theta is y over r, so that's 2 over -6. So I went to my calculator and plugged in inverse tan of 2 over -6, and what did it give me? It gave me -18 degrees, which I thought was a little odd because we know that -18 degrees would be like right here almost, down from that x-axis going negative, and it would be going there. Now that I drew that in, I'm hoping that you see the relationship between that answer that the calculator gave us and our answer. -18 degrees. I mean, this is -18 degrees. So what does that mean? If you remember from geometry, vertical angles, that means that this is 18 degrees as well. It has to do with how our calculator is programmed, that it gives us that -18. We're actually going to be talking about that in 13.7 at the end of this chapter. But this is one of those instances where reference angles kind of come into play. This is telling us theta prime. It gave us the reference angle. It told us 18 degrees, but that's not theta. What is theta then? Well, I look at it and say, whatever theta is plus my 18 degrees got me to 180. Got me to that other x-axis, subtract 18 on both sides, theta equals 162 degrees. And that looks more correct because it's almost to 180, it's in quadrant 2, so 162 degrees looks good there. So these, you might get a reference angle answer from your calculator, I guess is what I'm trying to say, and that's something you need to be aware of. All right, one more, and I want to do this one kind of together because it's a little unusual. Our point given was 0, 4. I know that x equals 0, I know that y equals 4, but I don't see my triangle because there is no triangle. It's pointing straight up. How do I draw a hypotenuse in that sense? And this is where the coordinate plane gives us a little more power. It's not all about the hypotenuse, okay? Remember, r is defined as, well, r squared, I should say, is defined as x squared plus y squared. R squared equals 0 squared plus 4 squared. R squared equals 16, R equals 4. Is that, I mean, does that kind of make sense in your mind? Because we always draw R as from the point back to the origin. So if we went 0 to the side and 4 up, I guess it does make sense that R equals 4. So what does that mean for these values? Sine is y over r. And so that is 4 over 4, which is just 1. And fortunately, cosecant is also going to be 1 then, because we flipped the 4 over 4. It's still 4 over 4. It's still 1. Cosine is x over r, which is 0 over 4, which is just 0. 0 over pretty much anything is 0. But then secant is where we run into a question mark, because if we flipped it, we would get 4 over 0. We know we can't divide by 0. Secant is undefined for this angle. We cannot divide by 0. Anytime we try to divide by 0, undefined. Which leads us into our y over x for tan. 4 over 0 is undefined for tangent, but then flip it for cotangent. 0 over 4 is going to be 0. And as for the bonus, what angle is this? We couldn't really do inverse tan necessarily because I don't know how to type undefined into my calculator. I could do inverse sine or inverse cosine potentially, but I'm hoping you might also just recognize that that's a 90-degree angle, just from knowing 0 degrees, 90 degrees, 180 degrees, you might recognize that as a 90-degree angle. So this is the kind of the long problems, honestly, the long problems from 13.3. It's a very loaded section and we're going through a lot, I know. But I'm hoping this makes sense. The new definitions of SOHCAHTOA, y over r, x over r, y over x, making sure you know those, how to use them, and how to, if we have a point in the coordinate plane, how to find that angle, find all the trig functions. So a couple more thoughts, just building on this idea. R is a distance. R is always positive. So x and y, though, as we know in the coordinate plane, can be positive or negative. So I like to just run through and think about where are my sine values going to be positive. I know that sine is y over r. And I know that if r is always positive, then I'm always going to say something divided by a positive number. Well, let's look in quadrant 1. In quadrant 1, the y's are going up. It's positive. Positive divided by a positive. Any sine value in quadrant 1 will be positive. What about quadrant 2? We're going up, so its y's are positive. Any sine value in quadrant 2 is going to be positive. Quadrant 3, our y's, we're going down, so it's negative. A negative divided by a positive. Any sine value in quadrant 3 is negative, and any sine value in quadrant 4 is negative. Because of the y coordinate, just whatever sign it is, divided by our positive r, that controls the sign, the SIGN sign of the sine value. Cosine. Cosines are related to x's. Again, r's are always positive, so I know I will be dividing by a positive every single time here. Cosines are the x's. Over in quadrant 1, the x's are positive, which means cosines must be positive there. In quadrant 2, we're going to the left. My x values are negative, and a negative divided by a positive is a negative. So any cosine value in quadrant 2 should be negative. Same in quadrant 3, my x's are negative. But in quadrant 4, I'm going to the right again. My x values are positive. A positive divided by a positive is a positive. What about tangent? Now we don't have an r we can count on being positive all the time. We have y's and x's which kind of change sometimes. So let's analyze them one by one. Quadrant 1. I'm going up in the y direction, that's positive. I'm going right in the x, so any tan value in quadrant 1 should be positive. Quadrant 2, I'm going up, but I'm going left, and a positive divided by a negative is a negative. Quadrant 3, I'm going down and left, and what is a negative divided by a negative number? A positive. Tangent in quadrant 3 is actually positive. And then in quadrant 4, my y is negative, I'm going down, but I am going to the right, and a negative divided by a positive will always be negative. So these 3 quick charts are not things you necessarily need to have memorized. But I like showing you this because it builds that understanding some more of saying, okay, so sine values are positive when y is positive, they're negative when y is negative. Cosine will be positive when x is positive, negative when x is negative. And then tangent is positive when the y's and x's have the same sign, SIGN, negative when they're different. And we will see this pattern play out many, many times. One more kind of coordinate planey problem before we get to something called the unit circle that's going to change your life as you know it. But right now, take a look at this problem. It says theta is an angle in standard position. Its terminal side is in quadrant 3. Tan of theta equals 3/4. And what is the exact value of cosine theta? And my hint there is draw a picture, which I'm always a fan of. Okay, theta is an angle in standard position. That means it starts right here. its terminal side is in quadrant 3. So I know it ends up here. And I'm told that tan theta, which is y over x, is 3 over 4. Now that sounds kind of easy because, well then, y is 3 and x is 4, and it just ends up right here, except that doesn't meet the quadrant criteria. So how could we have a tan theta being 3 over 4, but not in quadrant 1? Well, kind of based off what we just did, what if y wasn't actually 3? What if y was -3 and x was -4? Now it lands in quadrant 3. So something to be aware of, and think about those quadrants, think about those signs. This is where our point has to be, and our terminal side has to go through this point because it's in quadrant 3 and tan theta equals -3 over -4, which they simplified to 3/4, but we know better. It's negatives because quadrant 3. So awesome. I now know that my x value is -4, my y value is -3. What is my r? R squared equals -4 squared plus -3 squared. 16 plus 9, 25. So r squared equals 25, r equals 5. It's one of our nice 3, 4, 5 triangles. And so what is the exact value of cosine theta? Cosine theta equals x over r. -4/5. The hardest part of this problem, honestly, is probably figuring out where in the graph this terminal side lies. Where does this point lie based on the quadrant, based on the tan value? But this is hopefully a nice demo, a walkthrough of how you can do that. Okay. So I've been waiting all lesson, and it has been a long lesson to get here. And so if you need to pause, stop, take a quick break, stretch, so that you are fresh for this last segment of the lesson, please feel free to do so. But this is where it all becomes real. This is where we start learning the unit circle, which is absolutely just so important that you know. It's essential that you know it. And we're going to memorize every aspect of it. More on that later. This is just our introduction day. But what is the unit circle? Assuming you've stretched out and you're ready to go. The unit circle is a circle that has radius 1 and is centered at the origin. So radius 1 centered at the origin, and pretty much everything that we talk about in trigonometry from here on out is going to be based on this. So we're going to use this unit circle to figure out what tan of 60 degrees is. How? It's just a circle. I see 60 degrees there, that's great. And I'll try to actually hit 60, but if I'm a little bit off, you know about where I am. So 60 is right there. What is tangent of that? Well, here's how we're going to approach this, and it's actually everything we've talked about so far. I don't know what x is at the moment. I don't know what y is at the moment, but I do know that r is 1. And maybe more importantly, thinking back to 13:0, I know that this has to be a 30, 60, 90 triangle. A 30, 60, 90 triangle, a special right triangle. And if you remember, the hypotenuse was 2x is what we called it. The shorter leg was x, the longer leg was x root 3. So what does that mean for us? Well, then the shorter leg is half of the hypotenuse, so 1/2. The longer leg is 1/2 times root 3, so root 3 over 2. Now we know our x, our y, and our r. So what is tan 60 degrees? Well, tan 60 degrees, that's y over x. So root 3 over 2 over 1/2, dividing fractions, root 3 over 2 times 2 over 1, root 3 over 1, tangent of 60 degrees equals root 3. How did we get that? By knowing our special right triangles on the unit circle. And this is where things are going to start to thread together a little bit. Tangent of 60 degrees is root 3. Now, I want to pause because I know some people will do this. Say, can't I just type in tan 60 here? And the answer is yes. But if you tell me 1.732050808 is the answer on a quiz, on a test, on your homework, I'm going to say it's wrong because trig is always expressed in terms of radicals. We want exact answers in terms of radicals. And so root 3 is what you need to know. You need to know how to do this. Now, could you check your answer by saying, okay, I got root 3 working it by hand. Tan 60 is that. Is that the same as root 3? Yeah, check your answer that way. It's awesome. But make sure you know how to work this by hand on the unit circle. Let's look at another one. These problems go kind of quick. Cosine of 150 degrees. So drawing out my terminal side, trying to draw it somewhat nicely, forming my triangle. And so what kind of special right triangle is this? I have a note there that the reference angle of 50 is 30, right, to get back to 180. Well, that tells us that this also is a 30, 60, 90 triangle. And because we're on the unit circle, we know the radius is 1, which means the shorter edge is 1/2, and this longer edge is root 3 over 2, except it's going to the left, right? That x, that x side is going to the left, so negative root 3 over 2. We're asked, what is cosine of this? Well, cosine is x over r, which is negative root 3 over 2 over 1, and anything over 1 is just negative root 3 over 2. Is just itself. I guess I should finish that sentence. So cosine 150, so by hand I'm getting negative root 3 over 2. Oops, I forgot to make that negative. So I'll do that real quick. Insert a negative. Negative root 3 over 2 is that. Is that what cosine 150 is? Yep, 100% we got this right. Again, from our special right triangles that we spent a whole lesson, we added 13-0 in so that we would know it. Know those. What about cosecant 315 degrees? So 315 degrees, right there. Draw my triangle back to the x-axis. What is the reference angle here? How far do I need to go to get from 315 to 360? Well, it turns out 45 degrees, which means that this has to be a 45, 45, 90 triangle. And if you remember those, radius is 1. We had x, x, and x root 2. And so how do we find our x values? We say, well, we have to divide by root 2. I'll show it out the same way I did in 13-0. I said, okay, so x root 2 equals 1. We need to divide by root 2 on both sides. So x equals 1 over root 2, which we know we're going to multiply by that root 2 over root 2. X equals root 2 over 2. Be careful with your signs. Root 2 over 2, because we're going down, I'm going to call this one negative root 2 over 2. So what is cosecant? Well, cosecant is sine flipped, which means it's r over y, which means it's 1 over negative root 2 over 2, my y coordinate. Okay, So then that's 1 over 1 times negative 2 over root 2. And so we get negative 2 over root 2, which we multiply by root 2 on top and bottom, we get negative 2 root 2 over 2, or just negative root 2. I'm hoping this equals negative root 2 when I put it in my calculator. It's cosecant. We said it was 1 over sine. It's sine flipped. So 1 over sine 315. And does that match negative root 2? Yes, it does. So again, knowing that the reference angle was 45 degrees, that's what allowed us to say 45, 45, 90 triangle. And then we use some of our skills that we already have, but this is where it gets hard, guys, because you have to be good with chapter 7, radicals. You have to be really comfortable with them. You have to be comfortable with all of these chapter 13 skills we're learning. Chapter 13 skills such as the unit circle, angles, special right triangles, where do they end up? The x root 2 patterns. And copy dot flipping, I mean, dividing fractions. There's a lot that is now being tied together, and this is how math works when we get to this level. You have to be good at all of these skills so that you can now combine them in different ways and have an awesome chapter 13 problem like this not seem too bad. So if you remember, we had a chart, and we had a chart that I showed you guys, and it had 1/2 and root 3 over 2s and root 2 over 2s, and all of those came from special right triangles. So now you probably kind of understand where this chart is coming from. You could work it out at least. So what I would like you to do is take a look at these 5 problems, and I'm going to work them out and then talk through them. But I want you to pause them, and I want you to try them on your own. If the previous few made sense, try these on your own, because you're going to have to do a lot of these on your own here coming up. And so I'm going to pause the video, let you give it a shot. I'm going to, work them out, and then we will kind of talk through it. All right, so here we are, and I want to talk about these 5 problems. Again, this is such an important skill. The unit circle is kind of like factoring. You got to be able to do it. You got to be able to do it pretty quickly and very confidently. And so we're going to spend a lot of time making sure that we do feel good about this. So here's kind of where we stand. On the unit circle, and I'm going to make this statement right now, and then at the end of these 5 problems, if I don't forget, because radius is always 1, sine and cosine, which are y over radius and x over radius, respectively, will just be the y and x values. You might have picked up on that because dividing by 1 is nice. It's just whatever it is. There goes the bell. So on this first one, tan 120, and I kind of just sketched out, okay, so 120, that's where my triangle is. It's a 30, 60, 90, and you can see down here, I said, okay, radius is 1, negative 1/2 for my x, because I'm going to the left, positive root 3 over 2, that's the longer leg. And I know that from maybe my chart, or because I know special right triangles, it will be worth it to dedicate those values to memory. So I said, okay, tangent is y over x, that's root 3 over 2 over negative 1/2. Copy dot flip, we get negative root 3. Cosine 210, step 1 was figuring out where is 210. It's 30 degrees past 180. So it's a 30, 60, 90, x being negative root 3 over 2, y being negative 1/2, and the radius being 1 on the unit circle. So x over r for cosine is really just x over 1. It's just x, because the radius is always 1. So the x coordinate was negative root 3 over 2. That's my cosine value. My sine value for 300 degrees. 300 is 60 away from a full circle. Almost a full circle, but 60 away. So it's a 30, 60, 90. That downside is the long one, so negative root 3 over 2. X is 1/2 going to the right, radius is 1. Sine is y over r, but again, radius is 1. So we just take the y value, divide by 1, and we get -√3/2. Couple in radians, just for good measure, cosine of 7 pi over 4. So maybe the hardest part was figuring out where is 7 pi over 4. And I drew it in dark purple here on my graph. It's the same as 315 degrees. We've seen equations for converting, but 315 degrees. And so 315 is 45 away from 360. And so we know it's a 45, 45, 90 triangle. So those legs in the unit circle will always be √2/2. Maybe positive, maybe negative, but will always be √2/2. So we know that x's are positive because we went to the right, y's are negative because we went down. X over r, √2/2, over my 1 for the unit circle is just √2/2. And then tangent 11 pi over 4, it's more than a full circle, but it's a full circle plus 3 pi over 4. So that's another 45, 45, 90. I wrote down those side lengths, and y over x, √2/2, over -√2/2. Anything over itself is just 1. In this case, it's negative because we were positive divided by a negative. That might seem like a lot, and trust me, it is. This isn't easy, but we're going to do tons of repetition of this. You're going to have so much practice, and we're going to do more in class, and this is something that we just have to have in our back pocket, not even thinking about it. So a couple things I want to wrap up this very long lesson with, okay? The first one is that in a 30, 60, 90 triangle, on the unit circle, this only applies to the unit circle, but it will be well worth your while. I'm gonna draw this slightly differently, so it's in quadrant 1. Sorry about that. It will be well worth your while to know that the short leg is 1/2 and the long leg is √3/2. In a 30, 60, 90 in the unit circle, that is well worth memorizing. Similarly, in a 45, 45, 90, and I know these are not exact, I'm just sketching. On the unit circle, well worth your while to know that this is √2/2, and this is √2/2. The two legs are √2/2. That's a fantastic thing to know just off the top of your head. Okay, so long side in a 30, 60, 90, long leg is √3/2, short leg is 1/2. And that in a 45, 45, 90, √2/2. Also, worth it to know that in the unit circle, r is always 1. So sine is basically y. Cosine is basically x. We're going to have that in writing here in a lesson coming up soon, and I'll revisit that. But how do we just figure out trig values for these angles? What is tan 120? Well, you figure out that 120, passing period's over. You figure out that 120 is going to make a 30, 60, 90 triangle. You know the sides are 1/2 √3/2. You remember, okay, x's are negative there. And then you just do y over x. And this is how you can make flashcards. You can find online games, online quiz sites. But we're going to do a lot of this, including some timed assessments, to make sure you know how to do these problems quickly and accurately. 13.3 is maybe my favorite section. It's one of my favorite sections all year, because this is when trigonometry starts getting real. It was a long video, I know. I hope you broke it up into chunks. If you have questions, please bring them to me, because this is a really, really foundational piece for moving forward in trig, moving forward in math. But you're going to have some practice. Ask lots of questions. Check your answers on your calculator. Check your answers if they're provided. But 13.3, you made it through, and this is kind of small steps into a larger universe, as one would say. So hope this video went well. Rewatch it, rewind, ask questions, and I will talk to you later.